Okay, so today I have the pleasure of introducing John Simon as our colloquium speaker. John is a professor at the University of Chicago. He did his undergraduate studies at Caltech and received his PhD from Harvard for work that was actually done at MIT. And this was in particular pioneering work on developing single photon sources and quantum memories based on ensembles of laser-cooled atoms. For his postdoctoral work, he actually moved to Harvard and transitioned from quantum optics into quantum simulations, doing some of the really first quantum simulations of studying quantum magnetism in ultra-cold atoms trapped in optical lattices. And since 2012, he's been at the University of Chicago, and in his time there, he's been the recipient of numerous awards, young faculty awards from DARPA, the Department of Energy, the Air Force, and the President's Early Career Award for Science and Engineering. And for those of us who have known him since he was a graduate student, none of this comes as a surprise, because he's always full of creative ideas and the technical solutions to make them work.
You promised you wouldn't embarrass me, Monica.
So, so today he'll tell you about a very, very creative research program that sort of centers on defying the common idea that materials should be made of matter and instead building synthetic quantum materials out of light.
Thank you for that introduction, Monica. Perhaps excessively generous. I guess you'll get to make an assessment of that as this goes on. It's really a pleasure to be here. You want me to project? Is that better?
Well, I know you have a microphone over there.
I don't think that's a mic. I'll wear this though, and I'll try to speak loudly. So yeah, it's a pleasure to be here. What I'm going to tell you about today is ongoing work in my group and also in close collaboration with the group of Dave Schuster to make matter out of light. So before we even get into how that works, I think it makes sense to take a moment to talk briefly about what I mean by matter, what I mean by materials. So broadly speaking, I would say a material is a collection of particles that interact with one another and thereby organize or order. So what I have here is a really simple simulation. Each of these little dots is a particle that at large separations attracts the other particles and at small separations repels them. And I've added just a little bit of friction. Okay? So if you let this evolve, you get emergent order from very simple constituent objects, okay? So really, again, now what are the ingredients that we needed to make this happen? Well, the particles have to have some dispersion. That is to say, I have to be able to apply forces to them and have them change their speed and direction of motion, okay? They have to interact with one another. And then I need some way to suck entropy out of the system to cool it off into an ordered state. Okay, and so to make a material out of anything, we have to have objects with these properties. Okay, so if you were going to try to make matter out of light, the first thing you would notice is that if I have a massive particle and it's moving to the right, but I apply a force to the left, it slows down and then moves back to the left, right? If I have a photon that's moving to the right and I apply a force to the left, it doesn't slow down, its color just changes. So this immediately tells you that making a material out of photons is sort of by default sort of a questionable endeavor, right? So the first thing we're going to discover is that one way to understand this is to say that the dispersion of light is linear. Okay, and that is to say, as you change its momentum, its velocity doesn't really change. Okay, so if we trap our light in some sort of metamaterial, we can give it dispersion so that when we apply forces to it, its velocity can change. Okay? Question number 2, okay, how do we make photons interact? Well, what do I mean by interact? If I have electrons or atoms and I send them towards each other, they collide. If I have photons, what I discover is that, well, light basically obeys Maxwell's equations unless it's extremely intense. So one solution is a wave moving to the right, another solution is a wave moving to the left. Maxwell's equations are linear, so if I have a particle or a photon moving to the right and a photon moving to the left, or a classical wave, what have you, they just go straight through each other. So this, again, is not a great situation. And so we need to take inspiration from how electrons collide to make our photons collide. And the basic point is, electrons collide with each other by exchanging a virtual photon. So you might by default say, well, let's just turn that diagram around and have photons collide by exchanging a virtual electron. Well, unfortunately, this doesn't conserve charge, so that's not allowed. But you can draw a higher order diagram like this, which is allowed. Two photons come in, exchange essentially electron-positron pairs and go back out. And you can compute the cross-section for this process, which physically speaking is saying if one photon goes past the other, how focused down does it need to be to collide with near unity probability? And the answer is that for an optical photon, at about 1 eV of energy, it needs to have a cross-section of 10 to the negative 56 microns, which is somewhat below the diffraction limit. And so this is not very promising. But I think the interesting point to make here is that there's a mass of the electron in the denominator, okay? And the reason for this is that we're taking an optical photon and converting it into electron-positron pairs, okay? And so if my photon is much lower energy than these electrons, 1 eV versus 500 keV, you basically have this very far off shell. It's strongly suppressed, okay? But this does suggest to us that what we would like to do is, instead of creating off-shell atomic excitations, create on-shell atomic excitations. So what's the moral? The moral is the photons don't interact directly. The photons can be converted into matter excitations. The matter excitations can interact and get turned back into photons. Okay? And so what we'll need to do is find a matter excitation that's about the same energy as the photons, so that this process isn't so strongly suppressed. So broadly speaking, this is how we make photons collide. And the third challenge, I would say, is in some sense broader, which is this statement that a system which is more quantum generically has less damping. This is what, in some ways, more quantum means, right? Your system can build up entanglement. We can see quantum coherence. But if I have less damping, what happens to this model if I turn off all of the damping? It's like a horde of angry bees, or maybe angry graduate students, right? Didn't get cookies before the colloquium, right? But you can see the thing basically does not, never equilibrates, nothing sucks the entropy out of the system. But the challenge is, if we turn on dissipation, well, the environment that's sucking the entropy out is also making measurements of the system, okay? And so, is there some way to suck the entropy out in a controlled way that does not destroy quantum coherence? And we'll see sort of two solutions here. One is particle by particle assembly, and the other is sort of localized cooling of the many-body system. Okay, so to connect this to things that maybe you're a little more familiar with, in a solid state material, the particles that move around are electrons. They interact with each other through the Coulomb interaction, okay? And we can control their dispersion by trapping them in some periodic potential coming from an ionic lattice, right? That's the paradigm of solid state condensed matter physics. There's a whole community of people studying ultra-cold atoms as materials, or as material simulators, where the atoms interact with one another directly, and their individual particle dispersion is controlled by a lattice of laser beams that again creates a periodic potential. So what we're going to do is take some of these ideas, but instead of talking about interacting electrons or interacting atoms, we will take photons, trap them in a metamaterial to control their dispersion, okay, and then use carefully engineered sort of state-of-the-art quantum optic techniques to hybridize them with atoms and make them interact with each other. So broadly speaking, I think what I hope you take away from this is maybe something about the power of this quantum photonics toolkit for studying many-body physics, but I think in the specific cases of these stories, one can learn quite a bit about the microscopics of the models from how we build up interesting few or many-body states from objects that basically naturally want to go straight through each other. So the two platforms I'll talk about are bulk materials, that is to say continuum materials made of optical photons trapped in optical cavities. And these cavities control the dynamics of the individual photons, giving them mass, trapping them, applying effective magnetic fields to them. And then a second story, which I'll tell you only a little bit about at the end, is lattice gases of microwave photons, where the photons can hop from one lattice site to another in a superconducting quantum circuit and interact with one another through tools developed for quantum computing. And this second effort is a real collaborative effort between my group and Dave Schuster's. Okay, so the science that we want to talk about is fractional quantum Hall physics. Okay? So the challenge, as I told you, is we need to make the particles have the desired single particle properties. We need to make them interact in the right way, right? And then we have to make an interesting many-body state. So before we can talk about making a topological molecule or a Laughlin molecule of photons, the question is, what is a fractional quantum Hall state? So what fraction of you have taken topological many-body physics? That's what I expected.
I know the answer.
Yes. Okay. So we have a special guest who's going to go through these slides for me. I'm going to go to the restroom, and you're up, Bob. Okay. So this is sort of an experimentalist introduction to the quantum Hall effect and the fractional quantum Hall effect. So let's just hop right into it. So if I take a charged particle and I put it in a magnetic field, what happens? Well, I get little cyclotron orbits from the Lorentz force, right? And what we know is wherever I put that charged particle, I get the same little circular orbits, right? So in some kind of a physical sense, we've got real translational invariance in this system, okay? If I increase the velocity of the particle, the orbits get bigger, but the orbital frequency doesn't change. It's always this cyclotron frequency, okay? So the interesting thing now is that these two facts together tell us almost everything about the quantum mechanics of the individual particles, okay? The point is we've got some physical translational invariance, and since I only ever see dynamics at this cyclotron frequency, I also have discrete eigenstates. That is to say, eigenstates only at energies separated by multiples of this cyclotron frequency. Okay? So then on the quantum mechanical side, what I can say is I'm going to get families of eigenstates separated by this cyclotron frequency. Okay? And each family has some massive degeneracy which in some sense encodes the translational invariance of the system. Okay? Unfortunately, to conveniently talk about the many-body states, we're going to choose a basis for this family of states which is not translationally invariant. Okay? This set of states, this lowest energy set of states, is called the lowest Landau level. Okay? And we can write the eigenstates additionally as eigenstates of angular momentum. Okay? And so the point is these eigenstates are these either a dot or a ring of increasing size, okay? And the angular momentum essentially tells you how many units of 2 pi of phase winding you have around the ring, okay? So the thing that will be somewhat important shortly is that I can write the Lth eigenstate here as z to the L e to the minus z squared. So this is a 2D system, so what the heck is z? Well, z is x plus iy, okay? And this is sort of a magical thing that you can write the eigenstates in this notation. It makes things very simple. I've written it in terms of a single variable, which is a combination of the x coordinate and the y coordinate. And so what you can see essentially is z to the L is r to the L, e to the I L theta. Okay, so the r to the L piece moves me from a dot outwards in radius to a ring. In the e to the I L theta piece gives me L times 2 pi phase winding for these single particle wave functions. Okay? And I should say, feel free to stop me at any point if any of this is unclear. So imagine now my particles can collide with each other. The question you should ask yourself is, what kind of dynamics do I expect in this system? Okay? So classically, they're messy. I actually really wanted to make a classical numerical model, and I've tried to do it a number of times, but it turns out to be just really horrible. Once you add the interactions, it's just very unpleasant to do. So let's not do it. Quantum mechanically, the Hamiltonian looks like that, but let's not even worry about Hamiltonians. Let's go back to the physics, okay? Let's imagine that I have a bunch of particles living in this lowest Landau level, okay? And that they can collide with each other, which basically means that I pay some interaction energy when the particles are in the same location, okay? So the neat thing is you can think about this as generating collisions that conserve energy and angular momentum. Okay? So what that means is if I have a particle with 1 unit of angular momentum and a particle with 4 units of angular momentum, well, they can collide and become a particle with 2 units of angular momentum and a particle with 3. Or a particle with 0 and a particle with 5. Okay? So the question then is, if I have a whole bunch of particles living in these single particle eigenstates in the lowest Landau level, how do these particles collide with each other to produce a state of minimum energy? Okay? And so you can think of physically just pairwise they're colliding and hopping back and forth. It turns out the ground state for photons, anyway, which are bosons, okay, can be written like this. I don't know who this wave function is named after, but whoever it is a genius. But anyway, so let's see if we can just quickly understand why this is the many-body ground state. Okay? Well, the first thing you can see is that we pay no interaction energy in this wave function. Why do I pay no interaction energy? Well, if any pair of my particles are in the same location, that is to say if Zi equals Zj for any I and j, the wave function is 0. So the particles are never in the same place. Okay? So that's great. That says it's the ground state from an interaction perspective, but how do we know that this state lives in the lowest Landau level? Well, if you think of any particular particle, okay, that is to say, select Z4, okay, you're only going to get powers of Z4 times e to the minus magnitude of Z4 squared, like sums of terms like that in your wave function. And remember, Z sub 4 to any power is going to be one of those lowest Landau level wave functions, right? Z to the L, e to the minus magnitude of Z squared. So that says that this state is made up entirely of these lowest Landau level wave functions, okay? It has no interaction energy, so it's the ground state. Okay, so there are all sorts of neat signatures of this in the solid state. What we're going to try to do is build and validate that we've made this kind of a state out of photons. And on the one hand, see what we can learn about what one has to do that, and then also hopefully learn something interesting about the many-body states along the way. Okay, so the challenges then are going to be to engineer this Landau level for light, and to make the photons collide with each other and try to prepare this many-body ground state. Okay, let's hop forward. So, with that in mind, what does it then mean to make a material out of light? Well, what I want to say broadly here is that it means a lot of different things to a lot of different people. Okay? There are experiments where people make BECs of non-interacting photons, Bose-Einstein condensates of weakly interacting photons, 1D gases of strongly colliding photons, experiments, particularly those conducted here in Ben Lev's group and Monica Schleyer-Smith's group, where people study, I would say, even more exotic science, where the photons sort of aren't particles in real space. The experiments from Ben's group explore supermode condensation and let's see. So Ben's here. Let's see how I can describe his research without embarrassing myself. Basically, you can build all sorts of interesting network graphs of connectivities of modes and see what kinds of exotic emergent ordering one gets in atomic degrees of freedom mediated by light. There are beautiful experiments going on in Monica Schleyer-Smith's group allowing atoms, again, to interact with one another mediated by light in a cavity. So, again, why is all of this physics possible broadly with light? Well, the basic statement is photons move real fast, as you may be aware. And so, essentially, if you slow them down by coupling them to some medium, they can still be moving quickly in some other direction. And so what this basically means is that you can have light look to you like it's moving slowly, but really it's bouncing back and forth very quickly in some other direction. And this gives you fast degrees of freedom and slow degrees of freedom, which for expert allow you to make sort of effective theories with long-range kinds of couplings. So there's all kinds of really crazy stuff you can do with light. What I would say is we're going to be rather concrete here. We're going to think of our photons as particles, okay? And we're going to make them interact by trapping them in cavities and coupling them to atoms. So the central premise of the story, with the introduction out of the way, is that photons in multimode optical resonators behave as massive particles in harmonic traps. So what do I mean by this physically? Well, if I shine light into a cavity, these are my two cavity mirrors, I'll shine light in. My claim is that if you just watch the wave packet in the middle of the cavity, it will oscillate back and forth as though it's a massive trapped particle. So how does this work? Well, there we go. Okay, if I just ray trace the light as it moves back and forth in the cavity, okay, you can see that the slope of the ray is kind of like the velocity, and the length of the cavity tells me how much the slope translates into a displacement on each round trip. And the curvature of the mirror prevents the rays from just going off to infinity. It kind of focuses them back down. So the slope gives me some trapping. Okay? It turns out this is a nice qualitative picture, but the mapping is a little bit more exact and formal than that. The eigenstates of a harmonic oscillator, as we all know from freshman or sophomore quantum mechanics, I don't know what year it's done here, are Hermite-Gauss in space and uniformly spaced in energy. Okay? And for anyone who's ever made a gas laser, you know that the eigenmodes of an optical cavity with spherical mirrors are Hermite-Gauss in space and uniformly spaced in energy. Okay? So there is really a very direct mapping between these two stories. And so the picture you should now have in mind is if I shine the light into my cavity slightly off-center to one side, I can write this pulse inside of the cavity as a superposition of the lowest mode of the cavity and the first excited mode. And the point is these will interfere constructively on the right side and destructively on the left side to give me that bump off-center to the right. Okay? But they're at different energies, so some short time later, the plus sign will have turned into a minus sign, and the light will be off-center to the other side of the cavity. So this is a pretty simple picture of how this goes on. This is exactly how coherent states oscillate back and forth in harmonic oscillators, and indeed it's precisely the same story here for photons. Okay? And so what you should have in mind is that my light is delocalized everywhere along the cavity axis, because remember, I'm sort of coarse graining over the bounce back and forth motion and oscillating back and forth transversely. All right. So if you want more on how this works formally, we have a nice theory paper on the Floquet model. So the question is, what we've seen is that free space propagation between the mirrors essentially controls the mass of my photon. The longer I make the cavity, the more displacement I get on a round trip. Okay? The curvature of the mirrors gives me trapping. The question is there a way to make a synthetic magnetic field for the light, to make it experience a Lorentz force? Because remember, that's essential for making these Landau levels. And to answer that question, we have to go back to World War II submarine movies. No, seriously. So in the submarine movies, there's always a submarine captain with a periscope, right? Did you ever wonder why when you want to look that way with the periscope, you have to turn the whole thing? Why isn't there just a little crank that turns the top mirror? Well, the picture is this. Imagine I have two mirrors set up as shown here, and this is kind of how a periscope works. I'm looking at a tree, and the tree comes out vertical. If I rotate the top mirror with respect to the bottom mirror, the tree comes out rotated, okay? And so the picture you should now have in your mind is that as I rotate the top mirror relative to the bottom one, I can get any rotation that I want. And this is neat because now if I take these two mirrors and add two more mirrors to close this cavity, okay, on every round trip, the light gets rotated a little bit, okay? So think of a 4-mirror cavity like this, and I just twist it a little. So the picture you should have in your mind is that twisting the resonator out of the plane now turns the lab frame into a rotating frame. In addition to this massive harmonic oscillator dynamics we were talking about, additionally, I now have some rotation in the system. And now normally when I look at a particle oscillating in a harmonic trap and I'm rotating, right, I'm rotating around it, to understand what's going on, I should include a fictitious Coriolis force and a fictitious centrifugal force, right? The point here is that because the rotation is real, when we watch this in the lab frame, the Coriolis and centrifugal forces are now real. Okay? And so the point is the Coriolis force is like omega cross P, right? Which has the same form as V cross B. This just directly gives us our Lorentz force on the photons. And then the centrifugal force is a force that increases linearly with radius, right? Which is just the same as a harmonic anti-trap. So I can compensate for that with the curvature of my mirrors. Okay? So it looks like we now have a recipe to make magnetic fields for light. What you should have in mind is that I take a cavity, just a 4-mirror cavity that's planar, and this is again a numerical model where I start with this planar configuration so my particle just looks like it's trapped in a 2D harmonic trap, okay? So this is the single particle ground state. There are two single particle excited states, one excited along X and the other excited along Y. There are 3 doubly excited states, one excited twice along X, one excited twice along Y, one excited once along each axis. And now what we're going to do is we're going to twist this out of the plane, and we're going to see what happens to the single particle eigenstates and their energies. So here's your hint. These can't be the eigenstates once the cavity starts to twist. Why? Because remember I told you on a round trip, the image gets rotated a little bit. Right? And an eigenstate is something that doesn't change other than up to a phase under a round trip. So it's going to have to be at lowest order some superposition of these two that is the eigenstate. And it turns out this plus I times that is a ring. I saw somebody going like this, very nice. This plus I times that is a ring with 2 pi phase winding in that direction. And with a minus sign, the phase winding goes in the other direction. Okay? And the one with the phase winding that goes in the same direction goes down in energy. So if we watch what happens in the numerics, immediately the modes become rings. And when the twist produces just the right amount of centrifugal force to cancel the harmonic confinement from the mirror curvature, I get this Landau level.
Excuse me, this is
Yeah.
for light traveling in one direction only, yes?
This is for light traveling along the cavity. Oh, you're talking about the backward mode?
Yeah, the backward mode is forbidden, yes?
Yes. So what Bob is getting at is that this looks like it breaks time reversal symmetry, right? Magnetic fields break time reversal symmetry, but a mechanical structure like this that's undriven can't break time reversal symmetry, right? So the question is, how does it not break time reversal symmetry? And the answer is, if you follow the light around the cavity in a particular direction, you see a magnetic field essentially pointing along that direction. But if you follow the light around the cavity in the opposite direction, the cavity has another set of modes where the magnetic field points in the opposite direction. So this is sort of like a Z2 topological insulator for experts. What we do in practice is use our atoms to break the degeneracy between the forwards and backwards propagating light by optically pumping them. Okay, but we can skip that piece of the story for now. So this set of modes here is our lowest Landau level that we were trying to make. So this is an experimental talk, so I guess I should show some data. Basically, the game is to take super polished mirrors, like Ben or Monica use for their cavity QED experiments, and stick them into a 3D printed structure that's precision designed to give us exactly the right twist and length. This is the first data that we took showing that we get the physics that we expect. Experimentally, what we can do is tweak the cavity length slightly and watch the eigenmodes. So we can see the eigenmodes, and then this axis is their energy. Okay? And when we tune the length to exactly the right length, it gives us exactly the right amount of confinement, the modes become degenerate. And indeed, if you look closely, we can make all of these modes degenerate to within a couple of megahertz. And so this is what we call our lowest Landau level for light. Okay? Now, why is a couple of megahertz an important number? Well, the statement is that we're going to add interactions between the photons, right? And what we absolutely need is that the interactions are stronger than the energy difference between the modes, so that we have a situation where the interactions determine how the photons order, rather than just saying, well, this mode's the lowest energy mode, so all the photons should go there. Right? You'd like to be dominated by the interactions to see the interesting many-body states. So this tells us that we need interactions that are a few megahertz in scale to make topologically ordered states. So before going on, I'd just like to briefly highlight that one can directly measure the Chern number in this kind of a continuum system by essentially measuring the projector onto the lowest Landau level by sending light through this cavity and seeing what comes out on the other side. And you can do it as a function of position. And what this essentially allows you to do is view your cavity as a circulator with many inputs and many outputs, okay? And show that when I inject light into this region and look at what comes out there, and then inject it back in and look at what comes out here, and inject it back in and look at what comes out there, and compare that to the opposite, there's a quantized phase, okay? And the point is, in some sense, from this quantum optics perspective, that's just what a circulator does. Right? So as a quantum optics person, the fact that this thing has a non-zero Chern number is not so surprising. Right? And Kitaev has a nice formalism to describe this. We make these measurements and see that basically you don't have to do a Chern number measurement in momentum space, which is how one typically thinks about Chern numbers. One can make a local measurement, see that the system acts like a circulator, and that gives you this quantized Chern number. Okay, so our next challenge is that the photons don't interact. I guess I don't really need to do this demo because I already explained it earlier, but I did bring 2 laser pointers through security at the airport, so I'm going to do it anyway. Does anyone have a guess as to what happens when I cross the beams of these laser pointers? I'll give you a hint. It's super disappointing. Nothing happens, right? So that's a problem because we need to make our photons collide. We need to live in the Star Wars universe to make interesting many-body states of light. So the way we're going to do this is by using a technique called Rydberg electromagnetically induced transparency. And I thought I'd take a moment here to give you a flavor of how that works. So the basic point is that we need to use atoms to somehow make our photons interact with each other. So what's going to happen is I'm going to send light, the first photon will be this black photon, into an atomic medium. And I've organized the medium in such a way that whenever a photon goes into the medium, it's absorbed with very high likelihood by a big ensemble of atoms. That's the blue stuff, okay? And then, to make that happen, I have to use a low-lying excited state of the atom so that the atoms have a large absorption cross-section. Okay? But once that atom has absorbed this incoming photon, it's immediately excited by a very strong laser beam up to what's called a Rydberg state, an excited state with principal quantum number near 100 or 110. Okay? So where an atom in this 5p excited state has an electronic orbital that's at most a few nanometers in radius, in this 100 Rydberg state, the electronic orbital can be several microns in radius. Okay? So this is gigantic, and it's going to eventually allow us to make interactions between the photons. Okay, but the first photon, as you can see, when it comes in, it slows down. Why does it slow down? Well, it slows down because mostly it's not a photon when it's in the medium. Mostly it's an atomic excitation in my atomic cloud. Right? It gets absorbed by some atom and then re-emitted and then reabsorbed by another atom and re-emitted. And because this excited state is very long-lived, the light can move through very slowly. Okay? But here's the neat thing. Once one of the photons has been absorbed by the medium, these Rydberg electrons can interact with each other over many microns. Right? Because the electronic orbitals are huge. So when there's only one photon in the medium, there's only one Rydberg electron, so nothing interesting happens. The light just propagates through slowly. Okay? But when the second photon tries to come into the medium, what it sees is that basically it doesn't even see that there are atoms if it gets near the first photon. Okay? Because the interaction between the two Rydberg electrons shifts the excited state of the second atom many, many megahertz away. Okay? And so what that means is, once this black photon is in the medium, light that comes in near the first photon sees vacuum and moves through very quickly. But light that comes in far away from the first photon still sees the medium. Okay? So that's kind of like an index of refraction that varies with position. Okay? Which you should think of as like a lens. Okay? And so the point is, the first photon comes in and creates a lens for the second photon. And you can build a kind of an effective field theory where this is essentially collisions between the photons. Okay? So this is how we make our photons interact. And this is how we get this cross-section of like 100 microns squared for collisions between a pair of photons. Okay. So how does this look experimentally? We take a magneto-optically trapped gas of atoms. We load it into a lattice. We transport the atoms up into a 4-mirror cavity. Okay? And then inside of that cavity, the cavity mode propagates this way. This is a picture of the atomic cloud. We cool it down to half a microkelvin, 100 nanokelvin, something like that, in an elliptical trap, such that the gas is now very, very thin in this direction. And that's the direction that the cavity mode propagates in. And we don't want to have any dynamics in that direction. We want all the dynamics to be transverse. Okay? And so now we can do a whole bunch of different experiments here. The simplest experiment you can imagine doing is having not a cavity with all of these different modes, but just isolate a single mode of this cavity energetically from everything else. So for the experts, this is the transmission spectrum of the cavity. These two tiny little peaks here are the vacuum Rabi peaks. And this central peak is the EIT peak. This is where light goes through the cavity as a superposition of a photon and a Rydberg excitation, some atom which is excited to this 110s state. Okay? So the neat thing is if we send light through at this frequency, what we expect to happen is you should think of this object as like a quantum dot or a Coulomb blockade kind of system. The first photon can go in, but if I try to inject a second photon, it'll reflect off of the cavity. And the third photon and the fourth, they'll all reflect off until the first one leaves, and then another one can enter. Okay? So this first manifests itself as a nonlinearity. As I drive more and more and more strongly, the fractional transmission of these side peaks remains the same, but the central peak drops. And it drops when I have about one photon on average inside of the cavity. Okay? And so now I can look at the correlations of the photons coming out of the system, and I see that I can only have one photon come out at a time. This is what's called a G2 correlator. Okay, and what it tells me is, given that I just detected a photon coming out of the system, what's the probability as a function of time that I get another photon out at a time delay tau? Okay, and what you can see is for time delays of a few microseconds, I don't get another photon out. Okay, which means that there wasn't another photon in there. And this tells us the photons are anti-correlated nicely. So this is single mode physics. And it says we have very strong interactions between the photons. The cavity is, several microns on a side. Okay, it's a very macroscopic object, and it can only hold one photon at a time in this regime. Okay, so what I'd like to tell you about now is brand new data where we've actually managed to make sort of a minimal Laughlin molecule in this system by combining this twisted cavity and the strong interactions between the photons. So many is a sort of a generous statement. Is too many? You be the judge. Topological two-body states. Okay, so before we can talk about before I can show you the data, let's talk about what we expect to happen experimentally. And I have to say, so this idea comes from Jacopo Carosotto. And I just found it incredibly informative for thinking about what a fractional quantum Hall state is. So the picture is this. If I have this cavity, this is my L equals 0 state, L equals 1, and L equals 2, and I'm going to have local interactions between my photons. Okay? What happens when I inject light on the L equals 0 mode? Well, that's the experiment we just did, right? One photon goes in, no problem. But if I try to inject a second photon, the repulsion between the two photons due to these atoms in the cavity prevents the second one from going in, and I get a blockade, and the photons come out one at a time. Okay? So that's very nice. What happens if I try to perform the same experiment injecting light into the L equals 1 mode? Well, naively, I would have guessed two L equals 1 photons repel each other, right? And if they repel each other, the energy of two L equals 1 photons will be more than twice the energy of one. So I can't put two L equals 1 photons into the cavity. So I should still see a blockade. But here's the neat thing. Remember I told you that two L equals 1 photons can collide and become an L equals 0 photon and an L equals 2 photon. Right? So now the question you need to ask is not just what is the energy of two L equals 1 photons, but you also now need to ask, what's the energy of an L equals 0 photon and an L equals 2 photon, right? And is there some superposition of those two that has no interaction energy? Is it clear where this is going? Maybe not. Okay. So the picture you should have in your mind now is that this is our two-particle Laughlin state, as I wrote before. And I get terms that look like z1 squared times z2 to the 0, right? Well, that's z1 squared is a photon with 2 units of angular momentum. z2 to the 0 is a photon with 0 units of angular momentum, right? And then I get terms like Z1, Z2, which is 2 photons with 1 unit of angular momentum. Okay? So this is now very cool. This says that if I send in light in L equals 1, I can put 2 photons into the system due to the collisions, but they don't go in both to L equals 1. They go in a 2-particle Laughlin state, right? And so, or a bosonic 2-particle Laughlin state. For electrons, where the wave function has to be odd, this has to be an odd number there. Okay. So now I'll briefly tell you how we do this experimentally. What we do is we send light into this twisted cavity. We generate orbital angular momentum. Remember, the light has to go in with angular momentum so the 2 photons can collide. We generate that angular momentum with a deformable micromirror device, which is basically the object inside of that data projector. It gives our light angular momentum, okay? These photons with angular momentum go into this interacting system and should come out in 2-particle Laughlin states, okay? And so then at the output, what we can do is measure the angular momentum of each photon by, for experts, having cavities with different angular momentum states resonant for transmission and reflecting the light sequentially off of these different cavities with single photon detectors behind them. Okay? So experimentally, the first thing we do is we just look at the light coming out of the system, and we just look at correlations in all modes. And what we see is weak anti-bunching of the light. And now we can analyze this light coming out in all the modes, looking for correlations between the different orbital eigenstates. And what we see is that this is these, it's really not L equals 0, 1, 2 in our experiment. It's 3, 6, 9. But I'm going to call it 0, 1, and 2 because it will be less confusing, okay? So these are the L equals 1 photons. And what we see is that there's some suppression of getting 2 L equals 1 photons out of the system at the same time. But we can now also look at L equals 0 and 2 and look at correlations there. And what we see is that at 0 time, those come out in pairs. Whenever we get an L equals 0, we also get an L equals 2. And you can compare this rate. It's normalized in a weird way because these are cross-correlation functions for experts. You can compare this rate to that rate, and they're basically equal. Okay? So this says that we're essentially creating a superposition state like that, with more or less equal amplitudes to get 2 photons in this L equals 1 state, or a photon in L equals 0 and a photon in L equals 2. Okay? But the key point here is the following. Whether it's a Laughlin state or not depends critically on that phase. Okay? What do I mean by that? Well, if this phase is pi, then when you write down the 2-particle wave function, it keeps the particles away from each other, which was our initial objective, right? To create a 0 energy state where the particles avoid each other, right? If this is a plus sign, it keeps the particles in the same location, okay? And so here we have a very neat experiment. So what we're able to do, instead of measuring in angular momentum space, now we measure in real space, okay? So we look slightly off-center in this cavity at what happens when a photon comes out. We look for correlations in space. But the thing that we do that's neat is we slightly detune the single particle eigenstates from one another. We put this thing back in a trap, okay? And this gives us rotation due to the Magnus force. So what that means is after I detect my first photon, this hole should rotate around, okay? And it rotates around at about 100 megahertz. And so if I look at the anti-correlation between the photons, what I expect is a strong anti-correlation immediately after detecting the first photon that then becomes a correlation once I'm on the opposite side and then turns back into an anti-correlation. And that fixes this phase at pi. And that really says that we've made this 2-photon Laughlin molecule of light. So for experts, I did say that we're using L equals 369 instead of 012. This is because technically our cavity produces a Landau level on a cone, and the interactions between the photons are better when you stay away from the cone tip. And so the state that we produce actually looks like this, which I would say is a 2-photon bosonic Laughlin state on a cone with a quasi-hole at the origin. But the underlying physics is exactly what I just described. Okay, so I didn't start my timer at the beginning. How much time do I have? What time did we start? 10 minutes?
7 to 10.
7 to 10? Okay, so this is Emmy. She's my cat. And this is the intermission. Is everyone ready for another quick story? Is anyone ready for another quick story? Okay, well, I hope so. So we started with this question of what is a material, and we pointed out that we sort of need 3 properties. We need to be able to make the objects in the material act like particles. We need interactions, and we need a way to help the particles order, right? And so up to this point, the way we made this 2-photon Laughlin state was sort of by spectroscopically populating the zero energy state. What I'd like to show you very briefly is that it's actually possible to suck entropy out of a quantum many-body system made of photons. Okay? So the first point is this. We had this whole issue that if you don't have something to remove the entropy, right, you don't get to the many-body ground state. But then you ask, well, we always talk about solid-state materials, quantum materials. What do we mean that they're quantum? Well, what I would say fundamentally is that if I couple myself to a thermal reservoir locally, you expect that you're continuously measuring the system near the point where you coupled it. But as you get further and further away, the system acts more and more quantum, but you can still suck entropy out of the whole system through this local entropy dump. So this is just a little numerical model sped up, because it takes a while. But I only have damping here, okay? And yet, I can eventually stabilize this whole system into a crystalline phase. So what I'd like to show you is how to realize this in our circuit platform, and we will eventually transport these ideas over to the cold atoms. So the basic point is to develop a system where photons can hop around in a lattice, and if I put 2 of them on the same lattice site, I pay some interaction energy. Okay? So this is what's called the Bose-Hubbard model. Okay? And the interaction energy that I pay is U, and the particles hop from site to site with some tunneling rate J. What I'd like to ask then is, how do I stabilize this system in a many-body ground state with 1 particle per site? Now you might say, well, if the particles are photons, why don't you just shine a laser on the system and it should go to the many-body ground state? And that was my intuition at the beginning, but it turns out that's just totally incorrect. So why is that? Imagine I have a single one of these cavities and I shine a laser on it. Well, it starts out empty, and then I put a photon in, right? So far, everything's going great. That's what we wanted, to put a photon in. But then, my laser is shining on the cavity, right? So it will now stimulate the cavity to emit the photon. So now I don't have a photon in the cavity, right? And I sort of stabilize to half the time having one and half the time not. And if what I really wanted to do was create a situation where the ground state is 1 particle per site, this is not going to do that. That's going to create a very high entropy, high energy equilibrium state with some random number of particles per site. But a thing that will put 1 particle per site is if I can take this single site on the right, or left rather, and create a magical object that replenishes itself with a single particle whenever it's empty. Okay, but it's coupled to my system. So I put this single particle in there, and now it tunnels into my system, and now it refills itself. Well, this particle can't tunnel in because there's an interaction energy cost to you, and this photon's the wrong energy. This one can't tunnel back for the same reason, but a little bit of time later, that one will have randomly hopped over, and this can now hop back in. Okay? And you can fill up your many-body system in this way, and it turns out this kind of an approach works for stabilizing any incompressible phase of a many-body system. So we're going to talk about a very simple, classical-looking example of a Mott insulator, but this also works in principle for fractional quantum Hall states and so forth. So what does this look like experimentally? Well, experimentally, one side of our lattice is going to be an LC circuit. An LC circuit can hold 0 photons, or 1 photon, or 2, or 3, or 4. But the point is, each photon, if this is just an LC circuit, has the same energy. So I haven't generated interactions between my photons. But the whole circuit QED community is about making this thing nonlinear by replacing the inductor with a Josephson junction. Okay? So I can easily, and I say I, what I really mean is Dave Schuster, can easily put this Josephson junction in place of the inductor. And a Josephson junction is an inductor whose inductance depends very strongly on how much current is flowing through it. Okay? And so what this means is the first transition is maybe at 4.5 gigahertz, but the second will be at 4.2. So now I have 300 megahertz of attraction between my photons. Okay? So that's great. If I want to have them hop around, I can just make 2 of these things and couple them together with capacitors. Okay? So that gives me my tunneling. And in practice, we make that about 10 megahertz. Okay? And the important question is, what's the lifetime of a photon in this system? Well, the photons live for about 40 microseconds, which is time for about 12,000 collisions or 400 tunneling events. Okay? So this is a really cool system. This is our the circuit lattice microscope. These are the qubits, these LC resonators. We read out with these transmission lines the occupation of the individual lattice sites with single photon resolution. And the last piece we need to figure out is how to make that object. And for those of you who know laser theory, this should be very familiar. What I need to do is create an object which prefers to be in this first excited state. That is to say, I need to create a population inversion. Right? So I take one of these transmon qubits, and what I want to do is shorten the lifetime of the 2 photon state so that it decays quickly. And I'll do that by coupling this thing to a lossy cavity. And now I can drive myself from the ground state up to this doubly excited state and decay rapidly to the singly excited state. And this creates my, my population inversion. This thing constantly refills itself with a single excitation. Okay? And so in practice now, what happens, this is the chain. Each one of these what I'm going to show you is the temporal filling dynamics of this thing. The filling site is at this end, unfortunately. So if you watch, what happens is, by the end, after a few microseconds, the whole system is filled. It starts out empty, and you get this filling front that reflects back and forth. So this is a way of stabilizing a many-body state of strongly interacting photons. It's a technique that we intend to use also on the optical side to stabilize larger Laughlin puddles and hopefully eventually to do some anion braiding by these impurity interferometry techniques. And we can talk about that some more afterwards. So I think with that, I will just point to the folks in my group who really led this. Oh, I see. I have to click here. Great. So the circuit stuff was led by Alex Ma here, who's now faculty at Purdue, and was done in close collaboration with Dave Schuster. And the fractional quantum Hall stuff with optical photons, well, the twisted cavities were led entirely by Nathan Shine. These two have worked together very, very hard to make the fractional quantum Hall stuff go, combining those tools. So this is Logan Clark. He'll be on the job market next year. Keep an eye out for him. Very sharp man. So with that, I'll thank all of them and you for your attention.
Let's see, I want to ask about transition, about specific numbers. And so you answered one of them. The Q of the cavities is what? You said 10,000 circuits.
For the microwaves? For the stuff at the end?
For the line.
For the optical photons at the beginning. We typically work with finesses, which is the number of round trips here, of a few thousand. But one can go way up on that to improve the fidelity for larger many-body states.
Well, that was my question. It's an issue of you've got a decoherence. You're fighting decoherence, and that's one of them. That's one of the sources. That's the mirrors.
But we're not anywhere near the limits for the mirrors.
Well, where's the dissipation coming from? Is it the atoms?
The dissipation that we use to make the many-body states? Or?
No. If the Q isn't infinity, there's some damping somewhere.
So it's the transmission of the mirrors. We're dominated by the transmission of the mirrors, which lets us get our signals in and out. So fundamentally, the way to think about it, you can come up with a quantity which is more or less the optical depth of your atomic sample within the range for which the atoms interact with each other. And that number is enhanced by the number of round trips you get through your cavity. So we call this number the optical depth, okay? And it tells you how many collisions you get. The square root of that number is basically how many collisions you get before you have a decay event, okay?
Well, can I please follow up on this?
Yes, I apologize.
Your atom nonlinear medium is really sophisticated because you're pumping hard on it.
Mm-hmm.
And the pumping is very classical.
Mm-hmm.
It's high intensity, and it's a little bit black magic. So there's a number. How much of a loss hit is that nonlinear element costing?
It's a little hard to describe in those terms because the loss induced by this Rydberg EIT is energy dependent. Okay,
it's a very specific question. You don't have much light. Mm-hmm. 2 photons is not much light. Now, if you've got a loss, what will happen is most of the time the experiment will fail. Mm-hmm. No photon, 1 photon will come out. Mm-hmm. Okay, so how many failures?
Oh, that's what you're asking. What fraction of the time?
What fraction of the experiment of the photon pairs actually make it out and you get the test?
What fraction of the okay? I guess there are then 2 answers. One is what fraction of the time do we make a photon pair, right? Most of the time we probe the system weakly because we never want to have 3 because we don't have dissipative stabilization. So there it's a few percent, maybe 10%. And then the question is, of those photon pairs, what fraction of the time do they leak out,
yes.
Right? The photons leak out individually about 30% of the time. So the pair leaks out about 10% of the time. And then you can ask, what percentage of the time does the detector detect the photon that leaked out?
Well, we don't care about it.
Yeah. Does that more or less answer?
Yeah, so basically, you're losing a third of it, and so on those events where 2 photons are in the circuit, 30% of the time, one of the photons will die, and only one comes out. At best, one comes out, and that loss, that main loss channel, you say, is the mirror.
The main loss channel actually is that our cavity mirrors all have the same transmission.
Okay.
So most of the time it just comes out other mirrors.
Okay, so it's not the nonlinear medium.
So if you want to quantify the nonlinear medium, it's this optical depth number that ends up mattering. And what we get in these experiments, I expect, is about 4 or 5 collisions per lifetime.
I'm monopolizing it, but yes, I want to know that, but it's got a real and imaginary part. Okay, so the real part is the optical depth. It's the imaginary part.
The imaginary part. The imaginary part
is eating photons a lot or not, and you say it's not.
Not too much. But if we tried to make a 4-particle Laughlin state, that would be the dominant loss channel until we increase the cavity mirror reflectivity or increase the density of atoms.
Other questions?
So I was wondering, what is limiting the G2 of your measurements or for the 2-photon blockade thing? If you use, let's say, a true single photon source instead of weakly attenuated coherent like, would it improve these measurements?
So That's an interesting question. So what I would say is the G2s that I was showing you for the single mode data are not our most recent ones. There the G2 is like 0.01 or something. A single photon source would be incredibly useful because there are better protocols for making these many-body states where instead of injecting in the middle, you kind of put a particle in the lowest angular momentum state and then one in a higher one and let them collide into your many-body state. And then you can put a third one in an even higher angular momentum state. And if you have to inject coherent states, you're not injecting them into the right states. But if you could do it this other way, you would be. So yes, a single photon source would be beneficial. Do you have one for us?
Heredity.
What?
Other questions?
So tuning this cancel the centrifugal force. How well can that be done? I mean, how good is that?
Oops. So here you can see that they're canceled to like a megahertz or so for like 10 or 15 angular momentum states. Right? So the point is, essentially you can make the trap exactly zero, but disorder on your mirrors, astigmatism, what have you, leave you with a little bit of broadening even at the end. Okay?
Are there any last questions for John? Otherwise, let's thank him one more time.